Okay, so now in the first problem that we solved, we understood how to perform a static structural analysis by applying the boundary conditions and how to complete the procedure of pre-processing, solving, and then post-processing also. Okay. Now in the second problem, what we are going to do is we are going to perform an analysis on a steel bracket. Okay. Now you can see over here the boundary condition that have been applied. These two holes on the bracket are fixed support. It's not clear to you, but these two holes are fixed, and there is a load or there's a pressure acting on these two holes of 30 megapascals. Okay, you can see the dimensions of the bracket over here, so that even you can create the model and practice. Okay, so you can note down the dimensions of the model. Okay, after that you can see what we have to do. So once the boundary conditions have been applied, you need to check the deformed shape of the model. We have to calculate the factor of safety, and then we also have to remodel the bracket without these fillets, and we have to see what is the change in the principal stress and the 1 stress. Okay, so the first thing that we are going to do is we are going to create this model, okay, and then we will perform the analysis. So let us go to the software. So we will come to the software, and then we will add one static structural analysis system. Okay. Now according to our problem, the bracket is made up of steel. So in engineering data, you need to make sure that you have the structural steel material. After which we will come to the geometry and create the geometry. Now if you have the geometry ready, which is already created in a CAD software, you can import that geometry. So in this case, what we are going to do is I will import the geometry as I've already created it. Once the geometry is imported, enter into the geometry cell. Set your unit system and then generate the model. You can see that the model has been generated. Okay. Now study the geometry. Okay. Now once you get the geometry, always try to simplify the geometry wherever it is possible. Okay. That means if there is some optimization that we can do in this model, we should do it. So now if you look at the model very closely, you can see that it is a symmetrical model that we have. Symmetrical means if I cut the model into halves, it will not be wrong. Means this model is symmetrical about the ZX plane, plus it is symmetrical about the YZ plane. So what we can do is we can create the symmetrical model. Rather than taking the full model, I will take half of the model or 1/4 of the model. Okay. So let us create the symmetry, but before creating the symmetry, you need to see whether you have the planes. So now you can see all the planes are at the corner. I need in the center. So for that I need to create the new planes. I will click over here, and then the original plane should be the ZX plane, after which I need to transform it into the Z direction. You need to know this distance. So what I'm going to do over here is I will give the value as 5, no, it has to be equal to 5 or 50. You see it is exactly in the center. Now we will say generate. So I have that plane. You can also select this edge. See, okay, this total is 35. Okay, and now let us find out the length of this. This is also 100. So from here to the center it is going to be 50. So I will create one more plane, which should be the YZ plane. So I needed a new plane from plane. Base plane should be the YZ plane. I need to move in the Z direction, that is this direction, and the value should again be 50 units. And we will generate a plane. Okay. Now we will come to tools, symmetry, Number of planes I need is 2. I need 2 symmetry planes. The first symmetry plane is plane number 4 and the second symmetry plane is plane number 5. And we will say generate. You can see that we have got half of the model or 1/4 of the model. Now we will take this model for analysis. So I will close my design modeler and we will enter into the model cell. So you can see that you have entered into the model cell with the 1/4 model. Now once you come over here, first thing you need to ensure the material of the model. After which we will go into meshing and we'll create the meshing. So I will first perform the default meshing. Now you will observe that the meshing is not of good quality. So I can use the relevance options or the advanced size options or the default size. So let me give a default size of 5 mm and we will update the meshing. Okay. If you want to have finer meshing on the filleted areas or on the holes, you can refine the mesh again, or you can go for the proximity and curvature options. You can change your settings over here and you can update. So after using the proximity and curvature, you will observe that your meshing has become much more finer. Okay. Once the meshing has been done, we will come to the static structural node and then we will apply our boundary conditions. So according to the model is fixed at these 2 holes and there is a pressure acting at these 2 holes of 30 megapascal. Okay. So let us first apply the fixed support. You can see that the setting has been on the filter has been on edge, so I'll change it to face and I'll select my face. Now whenever you cut your model into half, let me explain it to you over here. Okay, imagine you have a plate with a hole. Okay, the plate is fixed over here and we have some loads acting on this face. Now because the plate is symmetrical, we can cut the plate like this and we can only take 1/4 of the section. So if I take 1/4 of the section, the model looks something like this. And I can apply my load over here. Okay. But where will you fix the model, because this area is not there in the model now. Now, whenever you create a symmetrical model, okay, you need to apply some constraints over here and over here. Why? Because practically, even if you have created 1/4 section, this area has to be considered. Okay, so the elements which are there on this face and the elements which are there on this face cannot move in this direction or this direction. That means the elements which are present over here cannot move in this direction. So what we can do is we can apply a displacement on this face and blocking this movement. Now suppose if this is your x direction and this is your y direction, then on this face I can apply a displacement saying that x movement should be blocked and y movement should be allowed. Similarly, I can select this face over here and I can say the displacement in y direction is 0. That means the elements over here cannot move in y direction. Okay. Now, because I have created a symmetric model using symmetry, you will observe that the symmetry region is available over here. So when you have created the symmetry, I don't need to worry about these constraints. But if you have created 1/4 model without using symmetry, then the displacements have to be given. Okay, please understand, if you have not used symmetry to create 1/4, you have from starting only, if you have created 1/4 of your model, then the displacement constraint has to be given. But in our situation, because we have used the symmetry, you can see the boundary condition is already applied. Symmetry region 1 and symmetry region 2. Okay, please understand this. So I don't need to apply these constraints again. Okay. Next, we will apply the pressure. Okay. So my fixed support is here, and now I need to apply the pressure. So pressure, I will select this hole over here, this whole area over here. Okay. And then I will give the value. So the value is 30 megapascal. Okay. And the pressure is acting on the whole piece. If you want to change the direction, you can also change the direction. Okay. Now there is one more thing that you need to know about forces and pressure. Whenever you are considering symmetry, I'll take the same example. Suppose the boundary condition that is acting is a force. Let us say the force is 100 Newton. Now whenever we apply a force on a face, the force will always get divided amongst the nodes that are available on this face. So if I see the side view of this, I will see something like this. I'll see a face on which we have the elements, and we will also have the nodes. So whatever force we have given gets distributed amongst the nodes. So if I cut half, or if I take 1/4, the force value will also reduce, because you are changing your area. This much area is gone now. So I don't have this much of area. So automatically what happens is the force value gets reduced. Okay. But when it is a pressure, suppose if this is a pressure, it gets applied on the entire area. So as the area gets divided, automatically the pressure will also get adjusted, and it will get applied. It will divide itself and it will get applied on this much of area. But when it is with respect to forces, forces will not get half. Forces will remain 100 Newton only, but it will get distributed only amongst this nodes. So automatically the load that is acting on these nodes will increase. But when it is pressure, pressure gets applied on the area. If area becomes half, pressure also becomes half. But that does not happen with forces. So whenever you are applying a force, and if you are going to consider 1/4 or half of this much of area, you should also divide this force by 2 if it is 2. So my force acting will be 50 newtons. Please make sure that whenever you are performing such kind of analysis, you give your boundary conditions accordingly. Okay. So now the fixed support is done, pressure is done, we have the symmetry region, and now we will add the solutions. So I need the equivalent stresses, I need the principal stresses, that is the maximum principal stress and the minimum principal stress, strains, deformations. We will solve the model. We will solve the model. After solving, we can check the results. So you can see that the stress generated inside this model is 55.087 megapascal. Total deformation is somewhere around 0.0025756 millimeters. Maximum principal stress is 33. Minimum principal stress is 0.044. Okay. In this problem, they have also mentioned that you need to calculate the factor of safety. Okay. Now, before we understand how to calculate it in Ansys Workbench, we will understand some concepts about factor of safety. Factor of safety is nothing but it is the structural capacity of a system beyond the actual loads. In other words, it is the ratio of the allowable working unit stress to the working stress. So if you check the formula, if Sm is the allowable working unit strength, that is the yield strength of a material, and Sw is the working stress, that is the calculated stress, Fs is the factor of safety. So the formula of factor of safety is Sm divided by Sw. Okay. If the calculated stress is lesser than the yield strength of the material, your design is safe. If the calculated stress is greater than the yield strength, your design is not safe. Okay. Now, factor of safety is generally calculated for materials. Now, depending on the materials, the calculations will also differ. Okay. For ductile materials, that is general metals that we use, for ductile materials, the equivalent stress is generally considered for calculating the factor of safety. So the formula is such that f of s is equal to sy divided by equivalent stress. Sy is nothing but the yield strength and your calculated stress, that is your von Mises stress. What is the von Mises stress? It is nothing but the equivalent stress. We will be studying about the equivalent stress in the coming sessions. But if the material that you are using is a brittle material, okay, the Mohr-Coulomb's theory, stress theory, is generally used for calculating the factor of safety. And this theory generally uses the ultimate tensile strength and the ultimate compressive strength for calculating the factor of safety, because the brittle materials do not have a specific yield point. Okay, because the brittle materials do not have a specific yield point, therefore we will use the ultimate tensile strength or the ultimate compressive strength for calculating the factor of safety. So if we are using a brittle material for our analysis, the factor of safety calculations will change according to this formula. So the formula is such that 1 upon factor of safety, that is f of s, is equal to sigma 1 divided by SUT plus sigma 3 plus SUC, where SUT is the ultimate tensile strength, sigma 3 is minimum principal stress, SUC is ultimate compressive strength, and sigma 1 is maximum principal stress. Okay, so let us do this now. So currently we are using structural steel material, which is a ductile material. So let me calculate the factor of safety. You can come to the stress tool over here. In tools, you can add the stress tool, and inside the stress tool you will see the factor of safety, and we can solve it. So you can see that the factor of safety is somewhere around 4.5383. Okay. So according to the formula that we have seen for ductile materials, the formula says that the factor of safety will be the yield strength of the material divided by the calculated stress. So if we check the yield strength of structural steel, it is 250 megapascals. Okay, and the equivalent stress that we have calculated is 55.087 megapascals. Okay, so if we say 250 divided by 55.087, your answer should be somewhere around 4.538. So let us see this. It's the same value that we have got. So that means the calculation that we've done is correct. Okay. Now we will understand if we are using a brittle material for our analysis, then how will we change the factor of safety calculation. So what I'm going to do over here is I will enter into engineering data, and I will add another material. Now aluminium alloy is not a brittle material, but I will consider this to be brittle, and I will apply, or I will enter the value of the compressive ultimate strength. If you see, the tensile ultimate strength is 310. I will give the same value for the compressive ultimate strength. Okay, and now we will again enter into the model. Once you enter into the model, we will change the material to aluminum alloy, which we are considering over here that it is brittle. Now, after we do that, we also need to change the theory. As we discussed in the PPT, that whenever we are using a brittle material, the Mohr-Coulomb's stress theory is generally used for calculating the factor of safety. So when you click on the stress tool, you will see in the details the theory. So here, instead of equivalent stress, I am going to use the Mohr-Coulomb stress theory, and the tensile limit should be according to the tensile ultimate strength and compressive ultimate strength. Okay, and then we will again do the calculations. So if you see over here now, the stress value is almost the same, but the factor of safety has changed. Can you see over here? Previously we had got a value of 4.53. Now the factor of safety is considerably low. That means the design is not safe if you are using a brittle material. Okay. If you want, you can note down this value and you can use this formula for calculating it manually. You will see that the answers will be same. Okay. So this is how we will calculate the factor of safety for a design using different theories. Okay. So now we have understood how to do the optimization in the geometry before the analysis. What are the points to be considered if you are applying pressure or forces? What are the constraints that you should apply if you are giving or if you are considering half of the model? And how to calculate the factor of safety. Okay. Now there is one more thing that we have to do, that is we have to remodel the design without the fillet. So what I will do is I will duplicate this analysis system. Okay. Once you get the duplicate of your previous system, now in this case, I need to change my geometry. So what change I want to make over here is that I want to delete the fillets. So I am going to come to create option and I will use the face delete option and select these two faces and we will say generate. So we have deleted the fillet. Okay. And then re-enter into the model. You will observe that the model has been changed. I will change my material to structural steel again. The meshing has to be regenerated because the model has changed. So I will first perform the meshing. You will see that the proximity and curvature is on because it was used in the previous system. Pressure value, fixed support, symmetry, everything remains the same. I just need to change my theory over here because again we are back into the ductile material and we will solve. Previously our stress value was 55.087. Now let us see what happens to the stresses. Okay, it is 55.4 in this area. Okay, we don't have much of a difference because the boundary condition is not acting in this area. Okay, it is not directly acting in this area. That is why I don't get any changes in this region. But you will surely see some change in the value. It has increased by some value. Similarly, the deformations factor of safety, okay, strain principal stresses, and the minimum principal stress. Okay. So that is the analysis that we have completed for the steel bracket. And we have also understood the factor of safety concept for different materials, that is for ductile materials and for brittle materials. Okay. The one thing that we need to discuss is the equivalent stress. Equivalent stress, if you see, we have a formula to calculate the equivalent stress, and equivalent stress actually considers the it is a combination, or it is the summation of all the principal stresses that we have. So the formula is something like this. We have the equivalent stress, which is square root of the principal stresses in every direction plus sigma 2 minus sigma 3 plus sigma 3 minus sigma 1 the whole square divided by 2. So this is the formula for the one Mises stress or the equivalent stress. Okay, and these sigma 1, sigma 2 and sigma 3 are maximum principal stresses, minimum principal stresses, and the middle principal stress. Okay, you can also see the same thing over here: maximum, middle, minimum. Okay, sigma 1, sigma 3, sigma 2. Okay, so this is what we have understood in the second problem.